When we need to use real valued numbers in our software, we use floating point numbers very often. Now, what we're going to do in this video is look at how we can represent floating point numbers, generally speaking, using scientific notation, how we convert from scientific notation to some form of binary representation of the same thing, and then we'll end with a brief bit of coverage about the primary floating point standard that we use in our languages today. So to start, let's remind ourselves of the basics of scientific notation, because this is where floating point numbers come from. So we might have a decimal scientific notation number like negative 3.78219 e to the positive 3. And when we write a number like this, we often do it because we don't want to have to write a whole bunch of zeros at the end, or maybe zeros at the beginning, because the scale of the value is particularly large or particularly small. And so it gives us a simplified notation. But when we write something like this, we can first of all understand that this E business, that really means is negative 3.78219 multiplied by an exponent of our base. So our base is 10 because it's decimal, and the exponent is positive 3. Now, when you are in decimal or in any base, and then you multiply a value by a power of the base itself, what that does is it relocates this radix point here, the decimal point in decimal, binary point in binary, etc. If the exponent is positive, then the relocation of this radix point will move in the right direction, because we'll effectively be scaling the number up. If the exponent is negative, we'll relocate the radix point so many positions to the left. Therefore, we are scaling the number down. So a number like this is really the same as negative, and I'll just write all the digits, 3.78219, and we would take the radix point here between the 3 and the 7 and move it to the right 3 positions. So it would go 1, 2, 3, and end up between the 2 and the 1. So really, when we write this number in scientific notation, this is the number that we need. Now, there are a lot of elements to the scientific notation, so we have to know what these are all called. The easiest of these, of course, is the sign. And it will have a familiar representation when we go to binary. Then we have this number here where the radix point lies. And this number is most accurately referred to as the significand. Significand. There we go. And typically, when we write numbers in scientific notation in decimal, we will also make sure that there is one digit to the left of the decimal point. At least that's pretty much a convention, and that's called a normalized number. It's a normalized scientific notation. And that one digit that's there is also referred to as the significand. Significant, meaning it's the most significant digit. So that's not to say that it means, say, 3 here, because in the end it really means 3,000. And if we would have had a negative exponent, this could be a small fractional element. But the idea is, coming from the most significant bits way off here on the left, which are all zeros, leading, or digits, which are all zeros, leading finally to the first digit of some significance, this is the most significant bit or digit. I'm sorry, I'm saying bits and digits interchangeably here. Terrible, terrible! But the significand has a significant digit. Over here, this is the exponent. And the E really just indicates that it's an exponent of the current base. So we have the exponent bits over here. All right, so now let's pick some kind of basic representation here. I'm going to section this section off. Let's look at how we could do this in binary. So we'll show an 8-bit floating point representation. So 8-bit floating point. And the reason we're going with 8-bit is not because it's particularly great, but because it doesn't have many bits, so we can show it pretty easily with drawing rather than a 64-bit thing. So if we have an 8-bit floating point, it's got to contain all of those same parts over here, right? And really, we don't even worry about the significant by itself, just the significand. All right, so we need the sign, significand, and the exponent. Now, it's really of no consequence where these things show up. But very often, especially since we're used to the sign bit being the high order bit, the sign bit, oops, that should be an S. The sign bit goes here, and it's just a single bit big. Then for these other locations, we have to decide how many bits of our remaining 7 bits we want to use for the significand or for the exponent. And realistically here, if we make the significant have lots of bits, then we'll have more bits of valuable data, but we'll reduce the size of the exponent field, which means we won't be able to scale the numbers very much larger than the significand itself, or very much smaller than the significand itself. If we go with larger numbers of exponent bits than significand bits, then we sort of put ourselves in the opposite situation. We can have a very large scale to our numbers, but we won't have very many bits of actual precision data or accurate data from the significand. So we have to sort of make decisions there. For our example here, I'm going to make the significand bits go here, and I'll just say that we'll make that bigger than the exponent, so we'll make these 4 bits, and then we'll have the exponent over here. The exponent will just use up the last 3 bits. So this is a totally viable floating point representation. But nonetheless, we still must understand how each of these parts work. So with the sign bit, we still have something very familiar, right? With the sign bit, we're looking at 0 meaning positive and 1 meaning negative. We don't have to, but that's probably what we'll do because we're so used to the sign bit. Having those 2 values represent those particular meanings. Then we have the significand. So in the significand, hard to speak and write that word at the same time for some reason. With the significand, we have some number of bits, right? So here we have 4 bits, but we might have n bits designated to the significand. And there's the lowest order bit of it, which would be in sort of the bit 0 position of the significand, and the highest order bit would be in the n-1th position. So I'm going to say we got bits a, n-1, and then bit a, n-2, all the way down to bit a sub 1, and then finally bit a sub 0. So for however many bits there are. In our case, I'm showing 4 bits, and we actually have 4 of those bits. So in our encoding, there will be these 4 individual zeros or ones, but how they are interpreted or what they represent could be done in multiple ways. And the 2 most common are to use a denormalized style. So denormalized, in which we really mean something like there's that first bit or the highest order bit of the significand bit, a sub n-1. Then there's the radix point. So the highest bit of the significand is sort of mentally thought of as sitting out here where this 3 is. Then there's the radix point, and then the remaining bits, a sub n-2, all the way to a sub 1 and a sub 0, are just copied after the radix point. Another way to think of this, if you're going to use a denormalized representation, or if you know that you're looking at one that's denormalized, so you can just take the bit pattern from the significand field, sometimes called the fractional field. You can write them down, and right after the first bit, you just insert a radix point. Very simple. Now, while this is a super simplistic representation, it has one flaw, and that's the flaw that the most significant bit could be a 0. And if that really is the most significant bit, then all the other bits that are to the left of it, right, higher order positions, would also be 0. And so it behooves us to wonder why we bothered to put the 0 in that most significant bit position, and why not go further down until we got something that wasn't 0, just like we have here in our decimal value, right? We don't typically write 0.37 whatever and then change the exponent to deal with it. We would put the 3 here. Now in binary, if it's not going to be 0, it can only be one thing, 1. So in binary, we can normalize and get an extra benefit. If we use a normalized representation like we do when we normally write scientific notation values in decimal, where there's a non-zero digit in the significant position, then that means it's got to be a 1, the significant bit. It's got to be a 1. So we don't actually even have to store it in the 8-bit pattern. We just know that there's a 1 floating around out there. And so we can insert it artificially. So in a normalized significand, when we're normalized, we would reinterpret this bit pattern in this way. We would know that there's a 1 floating out there, then a radix point, and then there would be 4 bits of data after the radix point, 4 bits of precision, including the n-1th bit, n-2th bit, all the way down to the 1st and 0th bits for however many bits we might have. And so as a side effect here, we gain an extra bit of representation. Now, this is really important, and it's a big gain, because if we would have put a 0 in that high order bit in our particular representation that only has 4-bit significance, then we would only really have 8 different values, 8 different bit patterns that have a 0 in that significant bit position. But if we assume there's a 1, then we get 4 bits to play with, and so we go from having 8 different bit patterns to 16 different bit patterns. So we gain quite a bit. The downside of a normalized representation, however, is if we assume there is always a 1 and then a radix point, how do you represent the value 0 by having all zeros? And the answer is you can't. You have to just predetermine in your standard that a particular bit pattern across all your bits means the number 0. So normalized does have at least that one drawback, but generally speaking, it gives us more bits of precision, which means more bits after the radix point, right? More bits on this side. And we get, as a side effect, more accurate values, at least in certain situations, not necessarily all. All right, then there is the exponent field. And there are 2 basic ways that the exponent can be dealt with. So with the exponent, the first way, and probably the most natural, is to use an unbiased form. So in an unbiased form, we basically just treat all these bits as if it was a 2's complement number. Right? And so for a 3-bit exponent, if we had a 0, 1, 0, we would assume that this is effectively the same thing as having written e plus 2, because this is the representation of positive 2. Or if we had 1, 1, 1, this is a negative value. So to figure out what the magnitude of that value is, we would want to negate this bit pattern with 2's complement negation. So that's flip all the bits, that's all zeros. Add 1 to all zeros and you get 1. So this is the bit pattern for negative 1. So you just treat the bits as if it were a 2's complement number by itself. Now the other way to do this is in a biased form, so obviously the opposite of unbiased. When we use a biased form representation, the generic way to do this, the grand scheme of all types of floating point things, is we take the bit pattern and assume that it is an unsigned integer value. So these are unsigned bits. And then we add to that some bias, which we'll represent as the letter B. And then that gives us what we can refer to as the true exponent. All right, so as an example, we might have a biased exponent representation with b being equal to -4. Then if we had 3 exponent bits here, let's say 0, 1, 0. We're going to treat this as an unsigned 3-bit number, and this is the number 2. And so that's going to be equal to 2, what this thing is, and then we'll just add the bias, so add -4, otherwise known as subtracting 4. And that means we really have e minus 2. Right? So the exponent is -2. Now if we use the same bit pattern here, 1, 1, 1, then that's really going to be, this is an unsigned value. This is no longer -1. This is 4 plus 2 plus 1, which is 7. But we're going to subtract 4 from it by adding the bias. And that will give us the same meaning as e plus 3. Now, in the standard floating point style that we use for most programming languages today, we don't typically add the bias b directly to the unsigned value contained in the bits. But that's because of that specific specification. Now, in the way we are doing things with this representation, if I give you a layout like this, and I say that it has a biased exponent where b equals -4, you're going to work it in just like this to figure out what specific bit patterns mean, or how to store a particular real valued number into those bits. Now, the important part about this bias is that -4 isn't actually stored anywhere. This is predetermined. Right. Predetermined by your standard. So it doesn't have to be stored, so we save the bits from it. But that is the way that goes. Now what I want to do is talk about the actual standard that we use for our floating point numbers in most of our modern programming languages. So that particular standard, straighten my papers, that particular standard is the IEEE standard, or IEEE specification or definition 754 for floating point numbers. Now, we're not going to do a ton with this. I just want to go over the basics of that representation. It's complicated enough and uses enough bits to where I don't feel like working through the individual bit patterns is going to gain us much over the discussion that we just had about the general floating point representations. But you should know a bit about what we have. So with IEEE 754, there's a number of different representations defined. One of those is what we call singles. And singles in, say, C are also known as floats. So a float variable in C or C++ is a single precision IEEE 754 floating point number. And they use 32 bits of storage. There is also double precision floating points. And there are several others. But these are the two primary ones that we deal with in modern programming languages. Not that those languages don't provide access to the others. But when you are wanting to use a double precision floating point number in, say, C or C++, that data type is called double. And it uses 64 bits of representation. And the double precision versus the single precision doesn't refer to 32 being doubled to 64, but rather the representational size in bits of our fractional portion. And so we'll take a quick look at those. In the single representation. Remember, this is 32 bits long, so this is some significantly long thing. And we have our sign bit here, much as we might expect. And then unlike the little version of a generic one that I just showed you, in the IEEE 754 standard, we put the exponent next. The exponent bits go here. This is 1 bit, and the exponent bits are 8 bits long. Right? Then we have the significand. Right? So that goes here, and that is 23 bits long. Right? Now, one of the things that we get out of this, first of all, we've got the sign here, so that's just as we expect, and it works just the way we might expect. But for the exponent, we have to know whether it's treated in an unbiased or a biased form. And so for the IEEE 754 standard, this is a biased representation where b equals negative 127. Now, technically, if you were to look that up, you would not see that the bias is negative 127. Instead, the bias would be listed as 127, which seemingly is very much not the same thing at all. However, the way it works in the IEEE standard for floating point is you would look at the value in the bit pattern as some particular unsigned number, and you would assume that it has already been scaled before being stored by the bias. So if you were to put the number 127, if you found that number in these bits in an IEEE 754 float, single precision value, then you would assume that that's already 127 larger than the true exponent. And so if you see encoded 127, it really means the exponent is 0. Right? So when, if you go back and look at how I want you to consider the generic version of a biased exponent, I want you to take the unsigned value of the bits and then add the predetermined bias to it. And the reason that I prefer that particular mechanism is because it has been used a lot throughout history in different ways and in independently implemented floating point representations, because it lets you manipulate the scale of numbers in a slightly different way. Right? But it is important to understand, at the very least, that the IEEE standard uses that bias before the bits are stored. So technically, the bias isn't negative 127, it's 127. I'm going to write negative 127 because what I would say is if you take whatever you get in these 8 bits and then add negative 127 to it, just like we did in our previous examples, that will actually give you the true exponent that was meant. Now here in the significand, we have to know whether it's denormalized or normalized. And the best thing I can say to make this brief is that this is mostly normalized. Right? So what I mean by that is that generally speaking, most of the numbers you're going to come across represented in a 32-bit float based on the IEEE 754 standard. Most of those numbers, the significand is going to be interpreted as if it were normalized, meaning that there was the extra 1. But the extra 1 does cause the problem of things like how do you represent the value 0? And so you can, of course, pick some bit pattern to mean 0. But you're going to have other representations that are very similar to it, like the same significant bit pattern but with a different exponent. And so in the IEEE standard, some of these unusual bit patterns are predetermined or predefined constant values like positive infinity, negative infinity. There's a value that means it's not really a number at all. And there's another value that means it's extra, extra, not really a number. The two differences are more along the lines of whether some value is one that can't be calculated or one that represents some kind of an illegal operation. They're just interpreted in different ways, right? But there are different bit patterns in the IEEE standard that are of a predetermined set that actually used a denormalized significand. And that's just to make it a little easier to represent numbers that we want to be particularly small, particularly close to 0, so between, say, 0 and 1 in the positive or negative direction. But for the grand scheme of these things, the very large percentage of them, the significand is just treated as a normalized value. Right. So then, if we compare this to the double, in the double we have the same thing. Here's a sign bit, and then there are exponent bits that are up here, and then we have the significant bits that are down here. But this whole thing is now 64 bits big, and so we have different number of bits. The sign is still just a single bit, but the exponent is now 11 bits long. And for this thing, it's still biased, but the bias is effectively negative 1023. Now again, much like this side, this bias here of negative 1023 is based on the way I've shown you floating point works. So if you take the bit pattern here and subtract 1023 from it, you'll get the true exponent. In reality, the way it's defined in the spec is that the bias is 1023, which is added to the true exponent before the bit pattern is stored. But this is, I think, a slightly simpler way to think about that. Which means that for the significant bit, we're left with considerably more bits to work with to show the fractional element of our real values. And so we have 52 bits here, which is slightly more than double the size of the representation in our single precision value. So this is much, much more precise in the sense of there are more bits after the radix point. Now the range for these, if we were looking at these, the ranges are extreme, really. So if we're talking about the single type, this one up here that is only 32 bits, there is the magnitude range. I'm going to make some absolute value signals here, mainly because whatever value you can represent, you can also have the negative of it by just changing the sign bit. So these things, the ranges mirror themselves about 0 on the number line. But we can go here from 1.2 e to the negative 38, all the way up to 3.4 e to the positive 38. Now, absolute value. On the double side, these, because we have more bits both for the exponent and for the significand, the range definitely increases. So our range now goes down to as small, as close to 0 as 2.3 e to the negative 308. All the way up to 1.70 to 308 also, yes. 308 also, I think. All right, so this is extremely large. This is really large too, but this is extremely large. And this is really, really small, but this is extremely small. So I guess this is a number very, very close to 0, whether it is positive or negative. So that's the basics of the IEEE standard for floating point representation. The last thing I want to do in this video, we'll leave the IEEE standard behind and just think floating point numbers in general, regardless of the representation. We have to understand that these numbers aren't stored just so that we have the number for later to print out. We want these numbers for doing calculations, arithmetic at the very least. So we should take a moment to understand the basics of arithmetic using floating point numbers. So let's do that. For arithmetic, we have two operations that are super closely tied to one another, and that's addition and subtraction. Right? I shouldn't use a plus when discussing these two. I'll use an ampersand. So there's addition and subtraction. And when we're going to do addition or subtraction, the first thing we have to do is ensure that the operands that we're using, the two numbers themselves, they need to have the same exponent. So we have to do some work to convert these operands to have the same exponent. Once we've done that, then we can finish up the operation by just adding or subtracting the significance, right? So we can add or subtract the significance. Multiplication is slightly trickier. So if we want to do multiplication, the first thing we do is we're going to multiply the significance, right? So we'll multiply the 6. Once that's done, and that means those bit patterns in isolation. Then we add the exponents to one another. Right? And then once that's done, we have a new result, and we need to normalize it again, meaning we effectively need to relocate that radix point so that we have a significant non-zero digit on average, if we're using at least a normalized representation. And all the rest of the bits of the significant are the bits after the radix point in the scientific notation version. So we renormalize if we need to. In some cases, we don't need to, but if we do it here. And then the final basic arithmetic, oops, I can't deal with having these all have uppercase letters and D in division being lowercase, so here we go. Let's say we're going to divide. If we're going to divide, it's similar to multiplication, but kind of in the opposite. So, or just converting multiplication to division in a way. So the first thing we do is we divide the significance, right? So again, just the two bit patterns themselves. We're not dealing directly with the signs or anything like that. Remember, this at least is nice for the division because the significance are like a magnitude in isolation, already with the sign removed, since that's in a completely different bit. Then, and this is where it kind of mirror images the multiplication, we're going to subtract our exponents because it is division. So we take the two exponent fields, subtract them in the order of the operation, and then we'll have a new exponent that we're going to deal with. And should we need to, we don't necessarily have to, but we may need to renormalize the bit pattern. Right. And that is it. So that's the basics of floating point representations. So we've looked at them abstractly, how we could do this in general. You know, we could put sign bit, significant, exponent, or we could have exponent, sign bit, significant. It's of no consequence, not really. It's an abstract form. We just need to have the bits grouped together so that we can use their meaning. We've looked at the IEEE 754 standard, so we know what we're dealing with when we're writing code in modern languages that are going to use that standard for sure. And we've looked at the basics of arithmetic operations. So if you have any questions, please let me know in the comments below. And in other videos related to this, we're going to look at examples of taking bit patterns and determining what they mean for a specific representation, as well as converting real valued numbers into bit patterns that we can store. And then we'll look at some of the issues, problems related to using floating point representations in general.